I'll just confirm with the audience. Can everybody hear me okay? And can everybody see the screen? Okay, sounds good. Okay, all right, wonderful. So yeah, I will also keep the chat window open here just at the bottom corner of my screen. So if there are any questions throughout the course of my presentation, please feel free to ask. And also, I'll leave some time at the end for some open Q&A after we finish with our topic here. So yeah, so hello and welcome. We'll get started. And the topic for this session that I'll be leading here is on demystifying machine learning and artificial intelligence. Actually, one thing that we'll start off with is even just first making the distinction between artificial intelligence and machine learning, because there are two actual technical terms that are kind of thrown a lot around as buzzwords. And so, yeah, my goal is to just kind of, give a very basic introduction to how modern artificial intelligence systems work, a little bit of the theory behind, how they have been developed, just so that we kind of get a better understanding of what these systems actually are, and how they can be created, what needs to be done to create them. So before we dive in, I'll share. I mean, yeah, we'll share these slides at the end. I don't want to spend too much time in introductions here. Just to give a little bit of background on who we are as an organization. So the coding school, which is the organization that I'm representing here, is a nonprofit. We've been kind of involved in emerging technology education for quite a while now, for the last 10 years. And we host a wide variety of programs for high school students, college students, educators at the college, university, and high school, middle school level. And again, we'll share these slides in it, so you can kind of feel free to have some more details at the end of this presentation also about the specific programs we have. But that's just a little bit about us. So we kind of have been focusing on this emerging technology space for several years. And one of our main branches is our AI education initiative, which is actually the part that I am with. And a little bit about me. So in relation to this, we have a year-long introduction to AI course that's taught at the high school level. So high school students all over the States. And this is the course that I've been teaching for the last 3 years. And yeah, essentially we kind of go from the very basics all the way to kind of what modern machine learning, deep learning, artificial intelligence looks like in this course over the course of 2 semesters. And that's just one of the programs that we offer. So we also have, like I said, many other workshops and programs that I'll have details on the slides at the end if you're interested in knowing more about those. Okay, and then a little bit about me, kind of outside of that also. At the same time, I am a graduate student at the Washington University of St. Louis, the School of Medicine. And my particular background actually focuses on the applications of AI and machine learning to medical imaging and cancer biology. So kind of the space of computer vision in general is the one that I have most expertise in terms of modern applications of AI. Okay. All right, so with that being said, let's just go ahead and jump right in to our topic for today. And I want to start just with a very basic explanation of what exactly machine learning is. And along with that, what is the difference between machine learning and artificial intelligence? So this will be an important distinction that I want to make. And before we even get into this, I think we all can kind of see that there's a lot of new technology that is around today that wasn't around 5, even 10 years ago. And I think it's fair to say that we're in the midst of a technological revolution, which in large part is developing with many new AI capabilities, right? Like I said, that have not been possible 5, 10, or certainly 15, 20 years ago. And we're at a time now, right, where it's quite extraordinary, where there are self-driving cars that can, at least in some jurisdictions, outperform human drivers with documented, evidence-based lower likelihoods of getting into injury-causing crashes. We also have AI systems that can be useful for performing medical diagnoses that may be challenging. or be able to detect diseases earlier than we have been able to before. We also have new AI systems that can aid even in agriculture, aiding precision development decisions about what crops to plant in which areas. And we also, even have systems that can interface with our nervous system to allow paralyzed individuals, for example, to play chess for their mind. So all of this is kind of quite remarkable technology, and all this technology is essentially a result of one or another type of artificial intelligence. And artificial intelligence, this is kind of the broad umbrella term for just this type of technology, any type of technology that seeks to mimic human behavior in some way, right? This is just what we generally think of artificial intelligence. So you can kind of think of many different definitions. I won't focus on one precise, correct definition of artificial intelligence, but it's generally any type of machine that is designed to simulate a human task, right? And that can be quite a wide variety of tasks, right? So, for example, a classic example that we often teach students is spam detection, right? Where in theory, you could have a human that would be sifting through emails and be making a decision of what email looks like spam, what email doesn't look like spam. And of course, today, pretty much every email inbox will have an automated spam filter that will do that automatically, right? And behind the scenes, there is an AI system, something that you could call an AI system that is performing that function, right? Self-driving cars, we mentioned. I'll actually come back to this slide at the end once we kind of understand a little bit more about how AI works and how we would create these types of systems. But the bottom line is that really these types of systems are all around us. And even if you, for example, are writing a web query, right, or going and doing a Google search for something, right, you will usually see, in addition to just the main search results on the results page, you'll see at the top, right now, Google will print out an AI summary, essentially some kind of an AI generated text to try and answer your query. Right? So, and that is its own type of AI system, right? That is trying to provide some kind of a response, some kind of written response to a prompt. So, any kind of simulating machine that is simulating human intelligence in some way, right? This is what we consider artificial intelligence. Now, it's important to understand that there are actually many different types of artificial intelligence. And the field of AI has kind of evolved quite a bit from its inception in, I'd say, in the middle of the 20th century. But what we kind of think of AI today actually really is machine learning. So machine learning is one type of AI, and it just kind of so happens that pretty much all of the modern AI systems actually are produced using machine learning. So this is what we'll get into next, actually defining what machine learning is specifically. But before we get there, I'll just mention an older type of artificial intelligence is what we call, we still use them today actually, what we call expert systems, where these are, if you wanted to develop, for example, a very simple type of chatbot, right, you could come up with a list of if-then statements or rules for this chatbot to follow. And it could be as simple as, if the user says hello, then respond with, hi, how are you, right? Or if the user asks, what is today's date, then respond with today's date, right? And if you came up with enough of these if-then rules, enough of these essentially expert-based rules for the system to follow, then you could produce something that you might consider to be artificial intelligence. Machine learning tried to go beyond that, right? And I would argue successfully went beyond that, right? Because with an expert system, you would naturally wonder, right, what happens then if the user asks something that there is no rule that covers that, right? It asks some new type of question that the designers of the system didn't think to include in the rule book, right? Then the system wouldn't know what to do, right? So that wouldn't be able to give a sensible response. So machine learning tried to solve that problem by essentially expanding to a new type of artificial intelligence, which is what the focus of this 1 hour session is going to be on. So nowadays, kind of machine learning and artificial intelligence are almost synonyms, just because pretty much all the AI that we have today really is built using machine learning. But expert systems do still have their kind of use in some niche circumstances. Okay, so now let's get into what machine learning actually is. And right, like I said, it's kind of trying to build an extension off of expert systems. And really the underlying goal was to design a type of AI where a machine could learn how to respond to different inputs without explicitly being told what to do, right? Without being given a rule book that the expert system would follow. And right, so for example, modern large language models like ChatGPT and other chatbots, right? These are an example of machine learning-based AI systems where when you give an input prompt to ChatGPT, there is no rule book it's following where, if the user gave this prompt, then respond with this, right? There's no rule book that it's following. It is literally has been trained from a massive amount of data, which you can think of as experience for this model, to be able to produce the responses without having explicitly been told how to respond to these different prompts, right? And at least on the surface, right, it appears very impressive, right? And it appears that all these large language models, they're able to produce very human, realistic text. But this is the underlying idea behind machine learning, right? And it's not just chatbots, right? Pretty much, like spam filters, right? They also are not following like rules that are set, right? In theory, you could probably come up with a set of rules for certain words to filter for, right? Or different like patterns of text or spelling mistakes maybe to try and make a spam filter. That's an expert system, right? That just follows rules. But nowadays, right, pretty much they're all using machine learning to do this. So not following any rules, but being given some kind of a data set, which the next part I'll elaborate on, to essentially make a machine learn through experience. Okay, so this is just abstractly the idea behind machine learning. This is what we will really dive deeper into in this session. So, right, machine learning, it's by now a pretty large subfield of artificial intelligence. There's the main takeaway our introduction there. Now, how does machine learning actually work? And right, like I said, it starts with a data set, right? So every machine learning model, right, and machine learning model, this is taken to mean an AI system that was built using machine learning. It is going to have been created using some kind of a data set, specifically called a training data set. And essentially, right, this is a bit of an oversimplification, but the way it works is the data set, the training data set is fed into the machine learning model, and then it will process that data. The word process there is actually, meaning doing a significant amount of mathematics and statistics to be able to learn, I'm saying learn in quotes there, patterns and relationships that are designed to allow the model to output what correct predictions would be for the given task. So we'll go through a lot of different examples of it, so you really get like a better idea of what this data set would actually look like. But this just at a high level is how it would work, right? You have some data set that is basically giving examples of what you want the model to learn how to do, right? And then you give this data set to the model. You don't like explicitly give the model a set of rules to follow for its task. You basically just give the model examples of the task you want it to accomplish. And then, right, using mathematics and statistics, we have algorithms that are able to learn, right, in some sense of the word learn from this data set to produce a trained machine learning model. And this trained machine learning model is what we would use out in the real world, right, as our spam filter or as our chatbot, right, to make either predictions or decisions or outputs based on different inputs. So actually, the first really key thing to understand, is, in my view, about machine learning systems is that pretty much in all cases, there is a very specific type of input that the model has been designed to take, and then a very specific type of output that the model is designed to predict or to return. And really fundamentally, the machine learning model is a mathematical function that takes, right? So I'll just kind of, I won't be drawing too much on here because we'll be sharing these slides, but right, essentially, if you think of the data as, usually symbolize it with X, and then its prediction or the output is some kind of y that we wanted to predict, right? The machine learning model literally is a function that is going to take in the input x and then, right, format it numerically so that it can mathematically predict an appropriate output given the task that we're dealing with, that the data is about. So it's just very, very general, right? You can apply this to a lot of different types of data. You can apply it to images, you can apply it to text, you can apply it to tabular data sets, you can apply it to time series, geospatial data, sound, video, pretty much any type of data that you can format numerically, you can use machine learning with. Okay, and again, we'll do many examples of kind of how this would work in practice and what this data set would look like. Right? But the bottom line, right, is yeah, this kind of approach of machine learning, right, it can be used again for a wide variety of data sets, for a wide variety of applications, right? Which anything you can collect data for, you can conceivably use machine learning with. Now, for this session in particular, I'm going to focus on image recognition. And I think once you understand kind of the principles that I'll outline in our examples here, then you'll be able to apply these same principles to other domains. Really, the only difference is going to be the type of data we're using and maybe the way that we're formatting the data numerically. So, of course, image data will look different from audio data, which will look different from a tabular data set or other data from other fields. But the principle is still the same of how we would design a machine learning system. Okay, so diving into computer vision, right? And just computer vision, obviously is just the field of specific type of machine learning, I would say, that's dealing with image-based tasks, right? So things that a human would conventionally be able to do to see an object and recognize what an object is, for example, trying to get a computer to do the same thing, right? Trying to develop this kind of computer vision capability. So if you actually step back and think about how our own brains process visual inputs, that this, I think, starts to give you some appreciation for how these computer vision systems work under the hood. Right, but of course, when you see, for example, this image of a cat, right, you will probably immediately recognize what this is. And if I then give you the same type of object, but just in different positions or with in different backgrounds, different circumstances, right, you'll still recognize these as all the same type of object, right? Those are all cats. And if you think about how you actually know what you're looking at, right? Because let's suppose I could be giving you a different type of animal or organism that you maybe have never seen before, and you may not then be able to recognize it if you've never seen it before. But if you actually think about how you know what you're looking at, the real mechanism that our brain is operating on is, pretty much your whole life, you've been consuming visual data, about just the everyday world around you, right? And presumably you've seen many examples of what a cat looks like throughout your life, right? Probably starting from an early age. And that is how you then know, right? Essentially your training data set is all of your visual interactions with a cat that you then kind of, subconsciously file away in your database of this is a cat, right? And so now, then when you see a cat, even if you've never seen this specific cat before, you will still be able to recognize this as a cat. Now, I will mention, right, if you imagine, suppose you see a cat with no hair, and maybe you've never seen a cat with no hair before, right? If you're presented with something that is a little bit outside of what you have been trained on, if you will, or what you've seen before, right, then you might be a little bit unsure, right? You might have to try and make an educated guess about what you are, what you're looking at, right? So, but by and large, right, we have kind of this very good generalization ability to be able to recognize that, obviously this is a cat if it's facing to the left or to the right, or if it's upside down or on its belly or what have you, right? So your brain, right, is learning from past experiences. And essentially, we want to instill this same capability in computers, right? So if we wanted to get a computer to do the same function, to look at images of cats and be able to recognize them as cats, right? And then also be able to look at images of things that are not cats and be able to recognize this is not a cat, right? And so, right, of course, you looking at this will know this is not a cat, right? And that's because we've seen many examples of cats and dogs throughout your life. And even though on the surface, they actually have many of the same features, right? The same, they have, furry ears, eyes, whiskers, a nose, right? But you kind of just know, right? Because you've seen enough differences between cats and dogs in your life to just automatically know the differences. So if we want to get the same type of behavior into a computer, right, using machine learning, then this is essentially what we would do. So first step would be to assemble a data set. And specifically, we would be looking for what's called a labeled data set, where we literally will compile a large volume of images of, right, again, images that represent the task we want the computer to learn how to do. And when I say labeled images, what I really mean is it's organized in such a way that there's very clear distinction between what the X is and what the Y is, if you will, right? So the X will be the input to the machine learning model. The Y is the desired output, the desired prediction or response. And right, in this case, right, the way it would be organized, you could have images, individual images of cats, right? And each one of those would be paired with the label cat, right? And then you might have images of other animals labeled with their own label as well, right? And so this is called a labeled training data set. Labeled because it has this very clear distinction between X and Y variables, essentially. And ideally, we want this training data set to be quite large, right? So, at least, as kind of as far as we can understand, a human can look at, can learn to recognize the difference between two different types of objects using, not really that many images, depending on the complexity of the task. Imagine that you're trying to learn the difference between a cat and a dog, and you've never seen cats and dogs before. You probably could tell the difference, given only a few dozen, maybe a few hundred images, right? You'd be able to do it pretty well. And actually, sometimes I do this experiment with students. I give them two different species of an Amazon parrot that, presumably there are no bird experts in the classroom. And right, they may not know that this is one species of parrot, this is another species of parrot, right? They just both look like parrots. But if I give you enough images and I label them as this is, species one, this is species two, and you start to notice, the color pattern, the differences in the shape of the beak or what have you, right? Then, I actually can show that you don't really need that many examples to then be able to do the task pretty well. And then say, okay, this is, if I gave you then a new image that you didn't see yet, and I ask you to tell me what it is, then very quickly you'll be able to tell what type of parrot you're looking at. So at least for computers, right, we need a much larger volume. So typically on the order of thousands or more of these images. But this is the idea, right? We compile this kind of a training data set. And then we put this into our machine learning model, right? And again, this machine learning model, it's a function, right? It is a function that is outputting. It's designed to take in whatever our input data is numerically. So we first have to format these images as numbers. And then it is going to produce our prediction, essentially, right? This thing is supposed to produce some output that we will then interpret as being out of a cat category or a dog category. And this trained machine learning model, this is essentially the thing that we would then use in the real world to distinguish between cats and dogs. Okay? So this is kind of the next key point I think to understand, right? That you need to have a training data set, and there needs to be a very clear distinction between what is the X variable and what is the Y variable. This essentially is true of all modern machine learning systems, even ChatGPT, which later I'll kind of expand on what exactly the X and Y is for a model like ChatGPT, or for a computer vision system in a self-driving car, or that would be used in a medical diagnosis from medical images. Right? There's always that the model is designed with a very clear definition of what its X and its Y variables are. Okay. So now once this model has been trained to tell the difference between cats and dogs, typically the way that these modern systems will work is they will kind of naturally pick up on what we might describe as features of the input data, essentially, right? So like if you think of features as the distinguishing characteristics that are separating your different categories, right? So if our two different categories are cat and dog, then right, you could come up with like a dichotomous key, for example, of just different features that you would write out, right? So this is like if you were to design an expert-based system, right? You might come up with this list of rules for a an AI system to follow, right, based on your own expertise on classifying cats and dogs. And right, the idea with modern machine learning systems, actually, they can learn these features autonomously from data. And they're able to do this with the help of kind of our modern mathematical and statistical methods that basically underlie machine learning algorithms. So the idea is, though, right, these learned features essentially become saved in the model. So this model you then can use every time it sees a new image, it basically is going through its inner mathematical workings of its prediction function to then look for essentially what features does it see in the input and comparing it to the features that it has learned about, if you will, to then make its prediction or its output response to what category this image belongs to. So now this model will be able to distinguish between cats and dogs, but this is another cautionary point that I'll point out about these systems. If you then give it images that it has never seen before, right? So if it was only trained on cats and dogs, but now you suddenly give it squirrels, rabbits, and parrots, right? These machine learning models, they do not natively have the ability to say, I don't know, right? Or I don't know what this is, right? So like if you give these to, right, and actually I do this with students also, where I give them 2 different species of parrot, right? And then I test them later on a 3rd type of parrot that I didn't train them on, right? That I didn't include in the training data, right? And I tell them one of your options is I don't know what this is, right? I haven't seen this before, right? And of course, as humans, right, we can kind of do that naturally, right? We kind of can say, I don't know, I haven't seen this before. But actually, it turns out it's kind of difficult mathematically to engineer the same behavior in a machine learning model. So this is one of the pitfalls, I would say, of these modern machine learning systems. They can sometimes lead to confidently incorrect predictions, right? Where it, because all it was trained on was cats and dogs, even if you give it something that is not a cat or a dog, it will may still confidently predict, right? I mean, a rabbit may have a lot of similar features to a cat, but it's not a cat, right? And so it's something to be careful of, especially, for in medical images, for example, right? There may be a lot of variance in the features that would appear on a medical image for a certain type of disease from patient to patient, right? Diseases can present in very different ways, and so you have to be careful with this, because if you have a trained model and then you're trying to use it in a real world on real medical images it's never seen before, right? It may kind of misinterpret just new features of this particular patient that didn't happen to be trained on. And lead it to make an incorrect prediction like this. But at least, this is the idea, right? The idea is to have this type of system then that can make these narrow predictions based on what it was trained.
Well, but then you have to use that card very often. Can't do it now, can't do it.
I'm not sure if someone's trying to answer the question, but okay. Okay. So all right, so let's continue. So right now, if you've wondered how, for example, your smartphone is recognizing your face if you use face detection to open your phone, or how a self-driving car would be operating, right? These are all using some type of a built-in computer vision system, right? In the case of a phone, there are AI models, there are computer vision models and trained models that are trained to detect the presence or the absence of a human face. So for example, if you give it an image with a human face, right, it will say there's a human face here, right? Or if you give it an image of an empty window, or an image of a water bottle or something without a human face in it, right, it will then tell you there's no human face, right? So essentially its 2 categories are either yes or no, there's a human face in the image. And then typically what will be done is that kind of a separate AI algorithm, a separate AI model that then is trained to specifically recognize your face, right? So once it's determined that there is a face, then there's another AI model that determines, is this your face or is this someone else's face? So you kind of combine multiple different AI models together here, multiple different machine learning models together to produce this more complex application. Self-driving cars, right? Typically, there will be cameras all over the car that are constantly getting live feed in from the outside world. And right, one of their functions may be to recognize different street signs, right? So you can imagine, going back here, we could have a training data set instead of cats and dogs of many different types of street signs. Remove the drawings here, right? We could have a training data set of many different types of street signs, of stop signs and construction signs, right? Speed limit signs, et cetera. And right, each of those is labeled with the type of sign that they are. And then this is one component of the self-driving car is this machine learning model that is essentially been trained to detect different types of street signs, right? So for all of these, right, once you kind of understand what your specific X and Y variables will be, what the input and the desired type of prediction for the model will be, right? In the case of unlocking a phone, right, kind of two separate models, both of them using an image as X, but in one case, the Y is just detecting yes or no, there is a human face. And another one is detecting yes or no, is it your face specifically, right? Then you can kind of start to build a framework for how to collect a data set that would be suitable to do this. Okay. So, right, and this is, the kind of technology that has been going on in the background, or even if we're not like aware when we unlock our phone, right, with our face that we're using a machine learning application, right, that is there. That is a new type of technology that we have. Okay. So, kind of just in summary, right, this is the specific subfield to computer vision, right, empowering machines with the ability to understand visual information the same way that humans do, so mimicking this type of a human task. And at least today, it really is an established subfield of machine learning, where, again, there are expert systems, right, so like expert systems, which would be examples of artificial intelligence that are not machine learning, right? Actually, the very earliest computer vision systems were expert systems, in fact, where there were specific patterns in images that would be basically given as functions to look for and detect to try and make a prediction about what is in the image. But yeah, nowadays, pretty much all of the modern computer vision applications are built using machine learning. And so this just to give another example, right, of a more specific type of computer vision, where this actually would be more like the kind of thing that would be happening in a self-driving car, but you would have your input, right? I'm going to draw the box around everything, but that whole image is the X, the input, and there are actually multiple desired outputs. So each of these little bounding boxes is a desired output from this image, right? And so, for example, in fact, you can break this down further into two separate outputs where I want to know not only that this is a dog, but I also want to know where that dog is, right? So typically the way it's set up is you have the model output as part of its prediction function, not just that this is a dog, but also like the XY coordinates of where the bounding box is that encloses that dog, right? Same thing for people, for signs, for traffic lights, right? And to do this in real time, kind of as you're dragging the car around, so the car knows what is in there. So more complex task, but still it can be broken down into these simpler components of X and Y input and output framework. And this would be, a model like this could be trained with a suitable training data set of many images like this, where, right, you have the image as the X variable, and then you have a collection of Y variables, collection of desired outputs, each of them indicating the type of object that is there, and also the XY coordinates of the bounding box around that object. And with a large enough data set, usually for these applications, usually many millions of images, you can create a system like this. Okay. So, right, then of course, these applications of computer vision are pretty much ubiquitous today. So, of course, used a lot in medical imaging, any kind of an automated checkout system relying on a visual inspection of a product will be using this. Of course, you can use this for security systems, face detection, matching with databases of people's faces to identify people, right? This can be an application of this. So lots of different applications of satellite images, any kind of image data, of course, will be has been used in some way to make a computer vision system. So what I want to do next is actually just kind of go through an example of kind of an exercise that we sometimes do with students, just to kind of see like, how would you, how could you build one of these rudimentary systems yourself, right? And so I'll use the example of astronomy, just to give you an example, like how would you collect a training data set and then actually train one of these models to be able to do a specific task in the area of images of outer space, astronomy. And so the specific task we'll do will be galaxy classification. And so just, brief astronomy background. Galaxies are essentially these large collections of star and other cosmic material, right, that have been gathered by their own gravity into some location. And astronomers will actually categorize them based on their shape into three main types, right? So, my alternative example to this was going to be different species of parrot, but to make this a little bit more interesting, I'm going to different types of galaxies, right? Where, it turns out astronomers will make a distinction between different types of galaxies. There are spiral galaxies, which have this kind of more, outer web-like structure. Elliptical galaxies, which don't have quite as much distant spirals and are less circular, they're more elongated. And irregular galaxies, which are just like clumps of matter without any necessarily organized structure. And essentially astronomers, they like to be able to classify different galaxies and understand the prevalence of different types of galaxies in the universe, right? Or in different sections of space that we're looking at. Do we see more spiral galaxies or more irregular galaxies? And the challenge here is that when of course, you could inspect each galaxy visually, right? And an expert astronomer could look at a close-up picture of a galaxy and be able to tell this is a spiral or this is an elliptical galaxy. But when we take, with modern telescopes, very high-resolution images of outer space, we can have to see many hundreds or thousands of galaxies. And so it's desirable to have some kind of system that can do this in an automated way, where we don't have to manually look at every single galaxy to classify it. We can have an AI system, a computer vision machine learning model that has been trained to classify different types of galaxies so that we can just quickly see the distribution of different types of galaxies just from a telescope image. Okay, so right, you kind of just think about this on your own, right? I'll kind of just keep going forward. Yeah, you kind of think about this on your own, just how would you do this yourself, right? Just kind of as a mental exercise, right? If you were to look at just different shapes of clouds in the sky, right? Similar kind of a task, or different types of galaxies, right? You can kind of think about how you would train yourself to do this, right? You would have some kind of a training data set, right? Where I would give you a galaxy zoo, if you will. And right, I would tell you that this is, for example, an elliptical galaxy. This is a spiral galaxy, right? These are irregular galaxies. I would give you essentially an example of what I want you to learn, right? An example of what, for a machine learning application, an example of what I want the machine to be able to do. And then this will constitute a training data set, where again, each of these images is its own observation. It's its own example, own training example, the X variable. And the Y variable is the type of galaxy, right? This will be the label that will apply to each of these images. They're elliptical, spiral, or irregular, right? And then you want to then get a computer to learn this in an automated way at scale, right? So that a computer can do this very quickly and accurately, so that we don't have to manually look at telescope images to then look at thousands of galaxies by hand, just to be able to tell what types of galaxies we're looking at. Right. So yeah, so basically, I kind of give a little more background here on just the types of telescope images that you can use in this type of training data set. And then I'll just kind of jump to the actual application that you can use to kind of do this on your own. It's kind of a new tool that actually has been developed in the last couple of years, where you can just go and kind of train your own machine learning systems using a training data set that you can collect yourself to be able to do a specific task. Right. So the goal will be to get a machine learning model trained on images to be able to apply the correct label to different types of galaxies. Okay. So the tool that I'll jump to the tool that we'll use here. And there's not really any connection here. This is just what we think is a good sometimes we use this for just instructional purposes. This tool called Teachable Machine. And this was, I think, newly developed in the last year or two by the Google Creative Lab. So I'll put a link in the chat, and we'll also have the link here in a future slide if you want to experiment with this with yourself. But I think actually it is a useful exercise just to kind of look through this and to see how this actually works in practice. And essentially you can go to this tool and it allows you to input different classes of images, different categories of images. And so, for example, here I have the elliptical type of galaxy. In this case, 123 images that I had uploaded previously. So these are all examples of of elliptical galaxies, right? And then I have the same type of thing for irregular galaxies. Here are an additional 117 images that we can upload that give an example of an irregular galaxy. And then, same thing for spiral galaxy. And, we kind of showed a little bit of variety here. Like we included this as a spiral galaxy, just to, maybe, like give it examples of a cat with no hair, right? In other words, to give it maybe less typical things so that it can maybe generalize better. And so, in principle, you can of course do this with any type of images, right? You can come up with your own classification. That's right. I could have done this with different species of parrots as well, right? Or any different street signs, recognizing, even detecting the presence or absence of cancer in a PET scan, for example. In theory, you could also do that here. Now, the caveat that I will mention, right, and this is, I think, one of the other main roadblocks, I would say, in kind of making this type of AI education more accessible. But it is actually very computationally expensive to train these systems. And so, for example, if you are working on self-driving cars, right, where these are all images of different types of street signs, and you have maybe 50 different types of street signs you want to recognize, right? And because you really want the system to work well, right, and like we said, a human can look at this and learn from a relatively small number of examples, but if to get a computer to do that, at least with the algorithms we have today, we really need a large number of training examples to get the computer to be able to tell the difference, with a reasonable degree of accuracy. And so, you can see how this might become computationally intensive, right? If I have 50 different categories, for each category, I have 10,000 different examples of street signs taken in different states on different types of roads, with different in the night and in the daytime, with snow in the background while it's raining, right, et cetera. Right, then I'm going to have quite a significant computational undertaking there to do. Right? So at least this tool, if you are going to train this yourself, just keep in mind that it will use your own local computer resources. So what I mean is it will use the computational resources of the actual computer you're using to run the web browser. There are other ways that you can use what's called cloud computing, where essentially you can utilize the computational resources of a company like Google or Amazon that basically they offer this as a service. They offer computational resources to people who want to train machine learning systems. And actually, in our own courses, we use a different tool called Google Colab, which essentially it's a similar kind of thing where you can train machine learning systems. You can also write like Python code, you can write computer code, but then you can train a model using what's called cloud computing, so that you don't have to use your own computer, which may not be able to handle this more intensive task. So for that reason, I won't actually train this model here because just from my own experience, training this has actually crashed my web browser here. So if I wanted to really do this on my own computer, I would probably need to have, start with just 2 different categories and a smaller number of images to make it more computationally manageable. But the idea is that, this kind of gives you a simple way to kind of drag and drop without, needing to understand the actual mathematical details of how the learning algorithm works, right? Or how, what the actual prediction function even looks like, right? Remember that this model, it's ultimately a prediction function. It's taking in the X as input, the images, and it's being trained to output the appropriate label, or we're defining these 3 labels as elliptical, irregular, and spiral. And so there is a mathematical prediction function the model is using to do that. And actually, right, this is one of the things that you would learn about if you go deeper into one of our other AI sessions that we offer. This is, for example, what we also teach in our year-long course to high school students. Actually, what the actual under the hood, what does this look like, right? So, what is an epoch, for example, a batch size, and learning rate? These are things that are outside the scope of what we can talk about here. But the idea is, right, you can actually go a little bit deeper into the mathematics of how this works. And in Google Colab, for example, right, which is the other tool, and I don't have it shown here, but it's the other tool like this. You can actually go further, and you can design more with more granularity these more lower level details. Right? But this actually, just as a resource, is I think pretty cool because at least I was not aware of this type of a interface being available even a couple of years ago, and it just gives you at least a clear example of how you would create a machine learning model, right? Of course, given that you have the computational resources to do that, then you can create a trained model, and then, right, in theory, if you had enough examples of different types of galaxies here, right, you can then use this for real and real telescope images to then classify the prevalence of different types of galaxies in different parts of the sky that we're looking at. So this is kind of the main application. Yeah, I'll put this in the chat. We have this up on a slide as well, but because we'll share these slides afterwards, and so you'll be able to see this if you want to interact with this tool later. Teachable machine. So yeah, so hopefully that kind of helps with at least giving a basic overview of what machine learning actually is, right? Just as a concept, and how, right? Again, this is a type of machine learning. This is a type of artificial intelligence, right? In theory, I could also make an expert-based system by coming up with a bunch of individual features of different galaxies, right? Like an elliptical galaxy might have, a certain eccentricity, right, that I could be trying to measure. Or regular galaxies, I could come up with different thresholds, different parameters to try and define different types of galaxies and use that as an expert-based system. Whereas the alternative here is using a machine learning approach, where I just give our machine learning model examples of what I want it to learn how to do, and then, right, it's using these more lower level mathematical and statistical algorithms to be able to create a prediction function that can take an image as input and then produce a reasonable output for what type of galaxy it is. Okay, yeah, so I will leave a little bit of time kind of in the last few minutes for questions, but I think what I want to just the last point to mention is not only why students should learn about AI, but also like what specifically I think is most important for students to learn when they are studying AI. And these are the kinds of things that we try to build into our own curriculum. Of course, it is a little bit challenging because the field is advancing so quickly that we actually regularly have to update our curriculum from year to year, just because of how quickly the forefront of modern artificial intelligence is advancing. A lot of kind of the older introductory techniques of the older versions of AI that were used 10 years ago, the older types of machine learning, those are still kind of the same, but we kind of have a lot of more advanced methods that are constantly being developed, right? And right, so of course, I don't need to kind of maybe convince everybody here of the importance of learning about AI, right? But of course, it is all around us, even though if we don't recognize that there is an AI system that is performing a facial recognition function to unlock our phone, right? Or if we are, interacting with an automated customer service, chatbot or voice bot, right? When we call a customer helpline, or when we, even if you use ChatGPT in your professional life, right? To sometimes people will use ChatGPT just to write a draft of something, and then, right, you're using an artificial intelligence, you're using a machine learning application there, right? So I think it is helpful to understand how these systems actually work, right? Given that they are essentially all around us. Right, but also, yeah, I mean, generally, a lot of different career trajectories are now more and more incorporating AI, right? For example, even in the legal field, right, there are legal specific AI applications that are being developed to be able to perform different tasks with legal documents. So if even if you are a lawyer and seemingly very far removed from the field of AI, right, you may still end up using AI tools in your day-to-day work, right? And for sure, this is only going to keep becoming more true as we keep going forward. But there are also, I think, a lot of ethical discussions that you can raise with these new uses of AI that, for example, there are lawsuits that are occasionally brought where some kind of an image generation AI, some kind of computer vision system, is using a large database of images as its training data set, and some of those images,
having a hard time working out. Well, guys, I found a surefire. It's not.
Sorry. Okay, sorry about that. But yeah, so I mean, bottom line, there are a lot of ethical discussions I think can be raised. For example, right, like I said, lawsuits where an AI system was using a training data set where actually some of the images there were created by artists, right, and were uploaded to the internet. And then from web scraping, these training data sets are created, and we create these computer vision systems that essentially, they can produce images that are in part, built on the training data set of like real artist, creations, right? And so then, right, there's a legal question. Do the artists have any kind of a claim to ownership of the images that this AI system creates, right? And, there's obviously, I'm not going to claim to know any right or wrong answers to these, but these are just, the new kinds of questions that we have to think about with the new kinds of AI capabilities that we have. Okay. Now, yeah, I will, just to kind of, I think, go back to our earlier example, because I did want to make sure to do this in our last few minutes before I open things up to questions, right? But I kind of just threw a lot of different, images here and called these different examples of artificial intelligence, right? And, right, I think the most important thing to take away from the session is that all of these systems, they are designed with some specific X and then Y framework, right? So for ChatGPT, right, it is designed this way, even though it seems to be a totally different type of system than a self-driving car, camera or a spam filter, right? It still actually works in the same way. The way that it is set up for a large language model is X is a prompt of text, right? So a prompt of text, which may be 10 words long, 1,000 words long, or maybe 5 words long. And then Y is just the very next word in that snippet of text, right? So like this is all the input, the X to that system, and the very next word is the desired output. And then you can generate, arbitrarily long sequences of text in this manner, right? Once you generate this next word, then that will become kind of the next input, right? That will become part of the input in the next iteration. And then I can just kind of, one word at a time, I can keep on adding to this prompt of text, right? And that's how large language models work. So the way that they are created is by scraping large amounts of text data from the internet, where from one Wikipedia page, you can very quickly make a large amount of training examples, right? I mean, if you just give it like one paragraph, I can split this paragraph into many different XY pairs, where X is just some arbitrarily long sequence of the text, and Y is just the next word immediately after that, right? And I can do that, like with an exponential amount of efficiency from just one paragraph, right? So this is why I think it's been pretty successful, these large language models, compared to for example, self-driving cars or any computer vision based systems. There seems to be computer vision. It's not quite as easy to like generate large amounts of training examples as it is for text like this. But this is just the example, right? To think about what the X and what the Y is for that specific AI application. Okay. So I will officially stop here. Again, we will share these slides afterwards, and we do have kind of just additional information at the end of the slide deck about different programs that we will offer. So I will not go through these here. I'll just kind of let participants look at these on your own if you're interested. But hopefully this was a helpful introduction to the really the whole field of machine learning today. It's its own field with very mature subfields within it. Computer vision, natural language processing, and it itself, machine learning, falls under the umbrella of artificial intelligence, right? And there was a time when the only kinds of artificial intelligence were expert-based systems, and machine learning was really not popular today. But today, pretty much all of the modern types of AI that are based on machine learning. Okay, so I will pause there, and then I noticed we do have some questions in the chat that I want to try to get to, and I'll ask, I think, 3 minutes here. But okay, so the first question that I saw, I'll just read it out because anyone is not able to see the chat. But the question is, how will people react to a mistake made by AI that causes harm to a person, even if it is 10 times safer than when the system is human controlled? Yes, I think that would fall under the category of different types of ethical or legal questions, right? To think about. For example, if you have a self-driving car that causes an accident, right? Who is liable for the damages resulting from an accident, or the injury, or if the loss of life happens? Who is liable for that, right? That's not something that I'll claim to have a right or wrong answer to. I think that's a legal question, that's an ethical question that we kind of need to decide, right? Because that can happen, right? Or if you have an AI system that is giving an incorrect medical diagnosis, right? Even if, like, on average, that diagnosis is more accurate than what a human doctor would be able to give, if the AI diagnosis is wrong, then who is at fault for that, right? Is it the fault of the developer or the doctor who's using that AI system, right? But the hospital that's using that AI system. So yeah, that is a question that definitely warrants some kind of discussion. The next question was, do you have any tips for helping students to understand generally limited size of the context window, given that the problems students like to explore often are larger, otherwise complex? So I think, is this referring to the large language models specifically? I mean, to ask for some clarification. Oh, most about large language models. Yeah, so at least for large language models, they are designed, actually, they're designed to take in a variable context window, right? So you can give ChatGPT just a single word as a prompt, and it will just do its thing, right? It will just take that single word as the X variable, and then the Y variable will be its next word that it's predicting. So yeah, I'm not sure if that answers the question, but for those systems, yeah, they can take in large or small context windows. Okay, so we are running out of time. I want to be respectful also to the rest of the program.